Okay,
Let's see.
it's here.
No, that's my Slack, but I can't see my pointer. Okay, there we go. It's down here. Okay. There. Okay, there we go. All right, so I put my journey through science on a map, and it's a slightly complicated map, but um so this is actually since I was born. So I was born here in Los Angeles, and then I moved to Salt Lake City and then back down to Southern California. That's this arrow. And then over to Austin here. This is when I was in middle school, and then up to Colorado. So we're right here, and then that's where I was before I came to RIT. And so now we're over here. I got my BS in imaging science in 2002, and I did a project involving speckle imaging of binary stars, and I really enjoyed the research and I really enjoyed astronomy. So I decided to try for a PhD in astronomy, but I did take a year off because while I was here, I also minored in Japanese. And so I went to Japan to teach it to be an assistant English teacher for a year. And I know that I put Japan geographically in the wrong place, but that's where it fit on the slide. And so then from Japan, I went on this long arrow, this long curvy arrow, over here to UC Santa Cruz, which is where I got my PhD in astronomy and astrophysics. And then from there, I went back down, and this is where it gets confusing, back down to quite right near where I was born. I was a postdoc at Caltech, specifically at the NASA Exoplanet Science Institute. And then I moved to Austin, Texas. I was a tenure track professor there, assistant professor for 4 years. And then in order to be in the same place as my husband, I took a job at Delaware. And so that's where I've been for almost 11 years. So that is my journey through the US and the world and science. So this is the background for the story I want to tell you today. This is the Drake equation, and it's not a mathematical equation that you can rigorously derive. It's rather a framework for thinking through this question of how many civilizations trying to communicate with us might be out there in the universe. And we can't actually explore the entire universe, but we can at least look at the galaxy that's near us. So this, on the left here, this is n, the number of civilizations that we could potentially communicate with. And then we have this big giant product. So this right here, R sub star, is the rate at which the galaxy has been forming stars. And that has most recently been measured to be about 1.9 solar masses per year. So this is one term in the Drake equation that we actually know. And then you multiply that by the fraction of those stars that host planets. And from the various surveys, pardon?
You're not sharing the screen.
Oh,
in the Zoom.
Oh, in the Zoom. Okay. Okay, let's do that. Yeah, the problem is I can't find the point. Oh, there it is. Okay. Okay. Okay, there we go. This is good. Sorry, it turned my mouse pointer very small when I plugged it into the display and I can't see it. So anyway, from surveys for transiting planets, so transiting planets are the ones that block some of the star's light, we know that basically all stars host planets. We don't know that for sure, but if you go ahead and do your correction for completeness and you take into account the systems that you can discover and then the ones you can't discover based on the ways that the planet orbits are tilted, what we can infer is that essentially every sun-like star has a planetary system. And this is something that we've learned in about the last decade. So that's really exciting. So now where are we in the Drake equation? We're on this third term here. This is what we're trying to measure now. So that is the average number of those planets that are hanging around the sun-like stars, that not necessarily sun-like, but all the stars that have an ecosystem. And in order to answer that question, what we would like to do is launch the Habitable Worlds Observatory, which should go up in the 2040s, which will let us actually take a picture of a planet and look at the reflected light from the planet, potentially see if there is a signature of a biosphere. Like, for example, is there oxygen in the atmosphere? On Earth, all the oxygen in our atmosphere comes from life forms. So potentially that's a biosignature. But before we can actually take a picture of the Earth-like planet, we have to know that it exists. And so finding that Earth-like planet is where my research comes in. So essentially what I'm trying to do is help with this third term in the Drake equation. And we are not yet close to figuring out what these other terms are. So the fraction of those planets that succeed in developing intelligent life, succeed in developing life, and then intelligent life. And it's an interesting question, what does intelligent mean? Because like an octopus, for example, is pretty intelligent. And then finally, can they actually communicate this civilization or this life that's on another planet? Can they send signals out into space? And then how long does that civilization last? Before it destroys itself, or the star destroys it, or a natural disaster destroys it. So that's our Drake equation. And if we know all these numbers and we multiply them together, then presumably we can answer the question, how many civilizations might be trying to communicate with us? We don't know all these numbers, but we're going to try to figure out this one. Okay. So how are we actually going to do this? I'm going to show you an animation of the radial velocity method. So what you see is here's a star in the center, and then there's a planet, and the star and the planet are orbiting their common center of mass, the barycenter. And as they're doing that, the star is wobbling toward us, towards you in the audience, and away from us. When it's wobbling away, you get a red shift of the light, a Doppler shift. And then when it's coming towards you, like now, you get a blue shift of the light. And so what we're looking for is an alternating red shift and a blue shift in the absorption lines in the star's spectrum. So I'll just play that one more time. What's really important is that mathematically, we often describe planetary systems as if the planet orbits the star. You can do that, but physically, they're orbiting their center of mass, which is important because otherwise we wouldn't be able to find the planets. But here the star is moving away from us. It's on a red shift. It comes around the other side of its orbit of the center of mass. Now we're on a blue shift, and we look for that alternating pattern. So we can see that in the velocity of the star. Okay. So that's great, but there are some problems. And so the first problem is we have parasitic signals. That's what this little rectangle says here. And if I look at it on my screen, then the rectangle is in front of the video, but it's not when it's projected. So anyway. Maybe imaging science people can fix that. So parasitic signal is something that we see when we measure the velocities, but it has nothing to do with the planet. And so I'm just going to play for you a movie from a solar observatory. And so in this movie, you can see, this is from the Solar Dynamics Observatory. You can see the sun rotating. You can see flares popping off in that movie. So if you look right here, for example, you can see a little flare going off there. All of these things, the rotation, the flaring, those give us a Doppler signal. So they give us a red shift or a blue shift, but it's not from the planet. It's from what's going on in the atmosphere of the star. So that's really unhelpful. We don't want noise sources in our data, but well, too bad. That's life. Let's see. Oh, come on. Okay, okay. So I'm going to play you another movie. This one is a zoom in of a smaller part of the sun. And what you're seeing here is convection. So you can see all these bubbles. You can see boiling upward, a rising of convective cells. And then in the dark parts, those are called the intergranular lanes. That's where you get falling of the cooler gas. So once again, we have rising and falling motions. That gives us red shifts and blue shifts, but they also have nothing to do with planets. This is called the pattern that you get from convective motions. It's called granulation, just in case you like vocabulary. So there are other types of parasitic signals, but these are the ones that I thought made the best, prettiest movies. Okay, we are going to shift to the next slide. Thank you. Okay, so what's a solution? Well, eventually we need to actually model out the noise from the stars. We need to actually be able to look at our radial velocity measurements and separate out how much comes from the star and how much comes from the planet. We're not there yet, but we can at least try to diagnose when we have a problem. Where do we have contamination from the star? And so one way that we can do that is with what's called an activity indicator. And then we have a statistical Fourier analysis tool that's called magnitude squared coherence. And if we combine these, then we can do, I think, a reasonable job of diagnosing the frequencies at which stellar noise is interfering with our ability to find planets. So what is an activity indicator? So this here is, it's a zoom in on the near ultraviolet part of a spectrum of a star. And this star is called Epsilon Eridani, and it's similar to the sun, but a little bit younger. So it's what the sun might have looked like when it was a teenage sun. And so if you look at the top two panels, you'll see very broad absorption lines. So no pointer that I can see. Okay, but anyway, you can see like the red fang rising upward, and the blue trough that the fang comes out of. Those are very broad absorption lines. And then in the center, that red fang pointing upward, that is emission from what we call the chromosphere of the star, which is the layer above the part that we see. And it's an area where you get a lot of magnetic energy release. And so when that happens, you end up getting emission in the very centers of these lines. So these lines come from ionized calcium atoms. And so if we look at this ultraviolet part of the spectrum and we see basically these red fangs coming upward, then we know that we're seeing a lot of magnetic activity. And we can measure the amount of light that we get in the red upward pointing fangs because the amount goes up and down depending on how much magnetic energy release is happening in the star chromosphere. And so by tracking that, we can get an idea of when magnetic activity in the star might be interfering with our velocity measurements. And then down on the bottom here, these red shaded regions, they're just areas of the star's spectrum that we compare to so that we can normalize our measurements of how much emission we have in the fangs. Okay, so this is called the S index. And these are some real measurements. On top here, we have, oh, thank you. Yes, that will probably help. So on top here, we have radial velocity measurements. So this is alternating redshift and blue shift. The convention is that you have a positive number, that's a redshift, a negative number is a blue shift. And then on the bottom, we have that S index that I was just telling you about. So it's a measurement of how much extra emission that we're getting from the chromosphere of the star due to magnetic energy release. And you look at this and you might say to yourself, I kind of maybe sort of see similar patterns of variability, and we can actually measure that. And this is the star. It's just an image of this particular, it's an M dwarf, so one of the very smallest stars in the sky, and it's called GJ 3942, just in case you needed to know that phone number. Okay. So what are we looking for? We're looking for oscillations that are shared. So if I go back here, I have my radial velocity and my activity indicator. If they share an oscillation at a certain period, that is a period where the signal comes from noise from the star and not from a planet. And so we want to take whatever we find at that frequency and say, don't call it a planet, it's coming from the star. So how do we do that? So here on the upper right, I've created two example time series. So one of them is my x of t. So my x of t is like my activity indicator. So it's just cosine of 2 pi t times this is an arbitrary rotation frequency that I picked. And then there's some noise in there. And so I gave it a rotation frequency of 1/25 cycles per day, which is very close to what the sun is. So this is like a sun-like star that's rotating. And then my y of t, this has both a rotation signal, and it's the same rotation period that I put in my x of t, which is my activity indicator, like the S index. And I also then put this planet signal in here. I put in a sinusoid to represent my planet, which has a frequency of f sub p. And I arbitrarily made that 1/80th of a cycle per day. So it's an 80-day period. So that's something between Mercury and Venus. And so one thing that people like to do if they want to see, is there a relationship between the activity indicator that's tracing magnetic energy release and the radial velocity, they might plot the radial velocity as a function of the activity indicator. So they simply put y sub t on the y-axis, x sub t on the x-axis, and they look at this plot. Sometimes the plot is informative. In this case, it is completely not informative. The reason it's not informative is, number one, there are two oscillations in my radial velocity series, my toy model that I made. I've got both rotation and a planet. And number two, I phase shifted the rotation signal. So in my pretend S index measurements, my x of t, I made it a cosine. I shifted the phase 90 degrees for the radial velocities. And we see that sometimes. So when we look at the same oscillation traced in different metrics, sometimes there's phase shift. And so what that phase shift means is that if this is the plot you make, y of t is a function of x of t, you get nothing, garbage, right? So you look at this and you say, oh, well, there's no relationship here. Activity and radial velocity in this star are not connected. You might look at this plot and conclude that stellar activity is not manifesting in the radial velocity time series. That is the incorrect conclusion. If you take a cross correlation of the two time series, you can see the shared oscillation, the rotation, beautifully. You can see that there. And you don't see the oscillation that they don't share. They don't share the planet oscillation, this f sub p. And that's what makes these so-called activity indicators so useful, is because the planets don't affect them. The planets only affect the radial velocity. The planets don't affect what's happening in the chromosphere of the star. So excellent. If we can look at a cross correlation of our two time series, we can diagnose, do they have a wave in common? Unfortunately, I have a huge problem. I can't straightforwardly calculate a cross correlation. And the reason for that is if I go back here, you'll notice that I have uneven time intervals between my observations. So in astronomy, we have to deal with the fact that here we are sitting on Earth's surface. The Earth is rotating, so I have to stop observing during the daytime. I can't see my star during the daytime. And then in some night times, you get bad weather, so you can't observe. Or some night times, maybe part of the sky is cloudy, but you can look in a different direction. So you have to change what target you're looking at. And then finally, we have to share our telescopes with people that study other things, like galaxies, for example. And so there are some parts of the year when we're not observing at all. And then we have the seasons. So from a given observatory, during a certain part of the year, you might not be able to observe a particular star. So that's why we have these big gaps. And then we also have these uneven time intervals between our observations, so we can't just take a cross correlation. And luckily, we have the frequency domain. The frequency domain is here to help us. So what we're going to measure is the magnitude squared coherence of our two time series. So you can kind of think of these two time series as one-dimensional images, and we're looking for oscillations that our two one-dimensional images share. And so this is the magnitude squared coherence statistic, and it looks scary, but it's not. So the numerator is a squared absolute value of a cross correlation estimate. So that's what this would be, but we measure it based on a non-uniform fast Fourier transform. So we use a Fourier transform for data that is unevenly spaced instead of with even spacing. And so that's how we get our numerator up here. And then our denominator is simply a product of power spectrum estimates. And so for here, we would have a power spectrum estimate from the x of t, which is our activity indicator, and then a power spectrum estimate from our y of t. And we simply take that ratio, and that ratio goes between 0 and 1. So up here on the top right, we have what's called a cross spectrum. So the cross spectrum is this thing on top that then gets absolute value squared. And you have a real part, which is plotted in black here, and an imaginary part, which is plotted in green. And for this particular cross spectrum, for my fake data set, all of the power is in the imaginary. And then I move to this statistic here, and it looks like this. And so it's a number between 0 and 1, and the closer you are to 1, the more likely it is that your two time series or your one-dimensional images share an oscillation. And so here you can see this is the rotation frequency that I put into my fake data set. And I recover that at a very high significance level in my magnitude squared coherence estimate. So this is my 0.01% false alarm threshold. So anything above this line is significant at above the 99.99% level. So I did a really good job at recovering the shared signal, despite the fact that there was a second signal and also noise in the data. I added noise. So this is a really useful diagnostic of when a wave is manifesting in both the activity indicator and the radial velocity, which means don't call this a planet. It's not, it's a stellar signal. And then we can also just do a phase estimate based on the ratio of the imaginary versus the real part of this spectrum. And when I did that, I recovered a 270 degrees at this frequency here, which is exactly what I put into it. So this method, I think, has a lot of potential to help us diagnose when are stellar signals interfering with our ability to find planets, and specifically at what frequencies is that happening. Okay, so here's an example. This is a real life star. It's called GJ581, and it's another one of those small dwarf stars. And for the X of T, I have, it's not the S index that I showed you before, it's H alpha instead. So you have a hydrogen atom with the electron jumping up from the second to the third level, and we can measure the strength of that absorption line. And that's a good tracer of the magnetic activity of the star. So that's my first time series, the activity indicator. The second one is the RV. And then these are the magnitude squared coherence on the y-axis, except I've just applied an inverse hyperbolic arctangent transformation to it. And what that does is it takes the coherent signals that are close to 1 and it stretches them out so they can go arbitrarily high. That means we can differentiate between very significant signals. So here are my different frequencies. And what you'll notice here, these labels D and G, these were planets that were reported. I'm going to put the planet in quotation marks. They were planet discoveries that were reported that were later shown to be false positives. So with other methods, astronomers looked at those and said, oh, those are actually not planets. And it was a little bit embarrassing, especially this one, G, because it was billed as the first ever Earth-like planet to be discovered, like a real honest to goodness Earth mass planet orbiting a sun-like star. Only it's not actually real. It's instead a harmonic of the star's rotation. And so what you can see here is I have plotted in blue is the coherence estimate, and then the horizontal lines are false alarm thresholds. So we have a 0.1% false alarm probability in red. And then we have an analytical and then a bootstrap estimate, which is why you see the wiggly and then the nice straight lines. Those two agree very well, luckily. And then we have 1% false alarm and then finally 5% false alarm probabilities. And then the dotted lines are the rotation harmonics. And so what you'll notice here is that so-called planets D and G are both sitting right on top of rotation harmonics. And at G, this magnitude squared coherence between the H alpha and the radial velocity is really high. We're almost hitting the 99.9% significance level, or 0.1% false alarm probability. And it's also pretty high over at the frequency of D as well. So D is another rotation harmonic. And I shaded these gold bands just because that's the resolution limit of my coherence estimate. And these gray bands, they're called C and B. So these are the frequencies of planets B and C. And we actually have a pretty clean coherence estimate here. There's not as much going on in the coherence between the activity indicator and the radial velocity. So this suggests that these planet discoveries are likely to be real, or at least there's no evidence that they are not real coming from the H alpha, whereas these are almost certain to be false positives. And what's really interesting is that I marked other rotation harmonics that were not misidentified as planets. So here, let's see. So this is, I want to say the third harmonic. This is the fourth harmonic and maybe the seventh, if I'm remembering correctly. We're seeing huge signals at these high order harmonics. So that is an indicator of how complex the star rotation signals really are. These little stars are very spotty. They have lots of spots on their surface, and so you can get a really interesting rotation signal. And this is something that I hope that stellar physicists will follow up on, is this fact that for these M dwarfs, the rotation signals, they go way up into the high harmonics. And did you have a question?
Is there a possibility of tidal locking or something?
So for tidal locking, you would need another companion to be very close to the star. And that's something that would be pretty easy to diagnose in the radial velocities and potentially also in an image. So we don't think that's what's going on here. This guy appears to be a star that's well separated from its neighbors. And so the harmonics then are probably just related to complex spot patterns, but you could definitely get that if you have a close binary. Okay. So here's another one. This is GJ3942. Again, one of these little M dwarfs. The M dwarfs are really tricky. Unfortunately, there's a big campaign to find planets around M dwarfs because it's easy to follow them up and measure their masses, but on the other hand, the stars are very difficult because they're very magnetically active and they have these complex spot patterns. So here we have the same kind of thing. What we have is planet B here, and then a possible second planet that was reported in a discovery paper. These look okay. There's nothing wrong here. But what's interesting is that the people who discovered these planets also measured the rotation period of the star. They measured it to be 16 days, but in our coherence between the H alpha and the RV, so same type of measurement as the last star, we do, yes, we see a shared oscillation peaking right up at 16 days, but we also see one at a period of 32 days at a frequency of 1/32. So an interesting question is, which one is the real rotation period? Is it the 32 days, the lower frequency, and this one is a harmonic? Or is potentially 16 days the real period and the 32 is a subharmonic? So we don't totally know the answer to that. My student, Andrew Fonseca, has been doing some follow-ups, and we're about ready to submit something, just a little short research note about this particular star. But it's interesting what you can find when you look into the magnitude squared coherence, because the rotation signals are a lot more complex than we might have thought. And even if nobody has misidentified either of these as a planet, we still need to know everything we can about the star in order to understand the planetary system. So we should know the rotation period. And it matters which one of these it really is. Okay. So now I'm going to transition from our diagnosing false positives using magnitude squared coherence into the power spectrum estimation problem. So here's our problem number 2 is we need a high quality power spectrum estimator. And so this on the left, we have a time series here, and we're looking at 2 types of power spectrum estimates, which I'll talk about in a second, but the measurements are pressures at the Black Forest Observatory in Germany. So they're atmospheric pressure measurements. And so this here is a naive periodogram, this P. So if you literally just do a discrete Fourier transform, absolute value, square it, that's what you get in the blue. And then in red here, this is something called the multitaper. And so what the multitaper aims to do is to suppress both bias and variance in your power spectrum estimate. So you can see the bias out here. The bias is the fact that the periodogram is higher than this multitaper by 7 orders of magnitude when you get to high frequencies. The reason for that is because information from low frequencies does not stay at low frequencies. When you calculate the naive periodogram, that power that belongs at low frequencies does what we call spectral leakage. It leaks out here. And so the further into the high frequencies you go, the more bias you get. So the bias is bad, but also if you look at the vertical excursions of this blue curve, you can see a lot of ups and downs. So the reason that this blue curve has this scalloped feature is not because they got creative with their graphics, but because there actually is quite a lot of variance here, and it makes a scallop pattern. Whereas if you look at the red, the multitaper power spectrum estimate, you don't have nearly that level of vertical excursions, really quick up and down excursions. So we definitely want to move from this, the periodogram, down to this multitaper. This is way better. And then this is just an example of the science they did with the multitaper power spectrum estimate, which I won't go into, but this plot, I think really sums up what are we trying to do with our power spectrum estimator. Okay, so we want to multitaper. Here's how it would work. These are Kepler spacecraft measurements from a star that this is its phone number up here, 6102338. And this is quarter zero. So this was actually engineering time on the Kepler telescope when they were just kind of making sure everything was working okay. What was great about quarter zero was there were almost no missing measurements. So in all the rest of the Kepler quarters, you have gaps due to things like thruster fires with the spacecraft, or maybe a piece of dust reflected light into the barrel of the spacecraft, and then it messed up your measurements and you had to cut them from your time series. But quarter zero had almost no missing measurements. There were only 16 out of 1,000 odd, so we just filled those in. And so after filling them in, what we got was a time series with regular observing cadence. So one observation every 30 minutes. Hallelujah. That's amazing for astronomy. And this is what it looks like. So this is just the brightness of the star as a function of a fancy way of counting time on the x-axis. And so what you would do with multitaper is these things up in the upper right, these are called tapers. And they are orthogonal to each other. So if you dot product any two of them, you're going to get a 0. And you take a taper and you multiply it by your time series, and then you compute the periodogram of that. And you do that for every taper. So this, I put 6 tapers up here. And so I take each taper and I multiply it by my time series. I get 6 independent estimates of my power spectrum. The shapes of the tapers suppress the bias, and then the fact that I get to average together 6 independent power spectrum estimates suppresses my variance. So I can squash both of those using multitaper. And then if you look on the lower right, this is a rendering of what's called the spectral window of the multitaper power spectrum estimator. So if you have a pure sinusoid, the spectral window tells you what kind of signal does that sinusoid produce in the frequency domain. And so you'll notice, first of all, this is a logarithmic x-axis on our frequencies. So this rectangle that you get, this upper part is actually quite narrow. And then we have a log scale on the y-axis. And this is only the positive frequencies because, log plot. So if you want to know what they look like in their kind of full shape, you can imagine reflecting this over the y-axis. But what's great is look at the dynamic range. So if I take this blue taper, this is my 0th order taper, I'm going from an amplitude of 10 to the 3rd all the way down to 10 to the -7 right here. So I got a factor of 10 to the 10 in dynamic range there, which means that if I have an oscillation, nothing but a sine wave, then my oscillation in my power spectrum estimate is the power is 10 orders of magnitude higher than just, the continuum around it, which is amazing. And the more complicated your taper, the less dynamic range you get. These numbers over here are called spectral concentrations, and they just measure, this is a measure of the spectral leakage. So all this power that's supposed to stay at one frequency, how much of it actually does stay at that frequency? That's this fraction over here, and these are high numbers. So they're very good at concentrating power where it's actually supposed to be in the periodogram, not letting it leak around. Okay. Here's the sub-problem of our periodogram problem. The sub-problem is the observing cadence problem again. So, unevenly spaced data, we see this all the time. That Kepler time series I showed you was really rare, the one with evenly spaced data. Here is a particularly pernicious spectral window. This particular time series comes from a large telescope that a lot of galaxy people like to use to look at their faint galaxies. Well, we're looking at bright stars, so we can do that during the full moon, but the galaxy people can't do that. The full moon will mess up their observations. So we planet people get all the observing time when the moon is full. And so here's the moon phase, 0 and 1 are full, half is new moon. And you can see our numbers of observations are very high around full moon. And so what does that do to our spectral window? Well, what it means is that instead of one nice, beautiful peak, we get this nasty pattern where we have a peak in the middle, and then on each side we have a pitchfork, and each little pitchfork time is at the synodic frequency of the moon. So this is plus moon frequency and this is minus moon frequency. So this weird observing cadence, it really messes with our results. Okay. So we're working our way up to dealing with this problem. Step one is multitaper for time series with missing data. So this is a different quarter from Kepler. That same star we looked at earlier, here we have some observations missing. And if you look down to this panel, this is a version of the multitapers. They looked very pretty in this plot. They're a little bit weirder in this plot, but they're still orthogonal tapers that have very high spectral concentrations. These numbers are close to 1. So here, the gaps in the time series are shaded here in gray. So we take each taper, we multiply it by the time series, we compute a periodogram, we average all those periodograms. This is what we get over here. This is our power spectrum estimate. And what we've done is we've used a statistical test called the harmonic F test to look for significant oscillations in that power spectrum estimate. And here we have 5 of them, and they are at 2 different rotation frequencies. So this is a differential rotator. It has more than 1 rotation period manifesting. And then it also has harmonics of both of those rotation frequencies. So this is a very complex rotation signal. Now, what we can do is we can take the ratio of the harmonic power to the fundamental power and use that as a proxy for whether the signal is coming from close to the equator or at higher latitudes. And what we find in this case is that the signal that's coming from close to the equator is actually the low frequency, long period signal. The sun is the opposite. So this is a rotation profile of the sun. At the equator of the sun, that's where it's fastest. It gets slower as you go up to the pole. This star seems to be the opposite. It's anti-solar, slower at the equator than the poles. Now, what does that mean for planet searches? It means that you don't want to take a noise model that's based on the sun and drop it in on this star. We do base our noise models on the sun because we try to select solar type stars, and so we kind of cross our fingers and hope it works, but you don't want to do that for an anti-solar rotator. Okay. Step 2 is coherence for these time series with missing data. So now let's suppose you don't just have 1 missing data time series, you got 2 of them. And so this is an example. We have measurements of the sun's Lyman alpha index coming from satellites, but there were times when there was no satellite looking at the sun with a UV filter. So we have some gaps in this time series. And then this is measurements down here of the magnetic disturbance storm time index, which is a measure of how much the Earth's equatorial ring current has been disturbed. And so we expect these to vary together because when the sun has an outburst, it disturbs the ring current. So, we expect waves in common. So we use these weird tapers for time series for missing data, and we do a multi-taper coherence estimate. That's over here. And the dashed lines are oscillations that we detect at a high significance level in our coherence estimate that also happen to be known oscillations in the sun. So we are seeing known oscillations in coherence in this magnitude squared coherence estimate for these 2 time series. So this is a mathematical demonstration, basically, that we can do real science with this technique, which is actually very new. So 2021 was when this multi-taper coherence for missing data method was derived. So this is really exciting. Finally, we want to go to full generality, which is when you deal with the real problem, the uneven observing cadence, not just the missing data. So these are measurements of the radial velocities of Barnard's star, which is the nearest halo star. It's a very, very old star, but it happens to be quite near us. Now we want to get multi-tapers for this data set so that we can do the multi-taper power spectrum estimates. What's tricky is that the way the tapers are calculated, these tapers here, is with a standard eigenvalue problem. The way they're calculated here is with a generalized eigenvalue problem that you have to solve for every frequency in your frequency grid. So instead of one standard eigenvalue problem, now you're doing thousands of generalized eigenvalue problems. Basically, you need a new set of tapers for every frequency. So that's why this is complicated and computationally intensive, and nobody's done it yet, but we're working on it. This is a set of tapers for this data, and these tapers are specifically for 0.005 cycles per day. So, a couple hundred days period that would probe. And we went ahead and we computed the multi-taper power spectrum estimate. And what I really like about this is that right here, there is a peak in the orange, which is a Lomb-Scargle periodogram. So it's basically, it's like the naive periodogram, except it's just made for time series on an uneven grid instead of even spacing. So here's this peak that was labeled as a planet, which through other methods, another team went back and said, actually, no, that's not a planet. And what we find with our multi-taper power spectrum estimate is you don't get a peak there. So we don't have to do all these expensive follow-up observations to say, no, actually, there's no planet. We just don't have the spurious peak in our power spectrum estimate. So this is in preparation. We're really excited about this. And it's also really hard. So that the effort is in making a usable software package that people can actually work with. But this is ultimately where we're trying to go with the multi-taper method. Okay, so I only have a little bit of time, but my two interesting imaging techniques, the first one is bolometry. So I'm moving away from time series and just fun imaging. So this is the Herschel Space Observatory. It observed from 2010 to 2013. And it was a far infrared observatory. And the way it observed was it did this scan and cross-scan pattern across the sky. So you had several detectors. They're bolometers. So you get a temperature change on the detector based on the amount of light you have. And then that temperature change is recorded. They have persistence, however, when the detector, when you're scanning across the sky in this scan pattern, when you move on to a new section of sky, you haven't completely erased the signal from the previous section. So that's what persistence is. And you can see that here. So these are maps of, I forget nebula. I think it might be the Flame Nebula. The start of the scans are over here where it's dark. The end of the scans are up here where it's very bright. And you're seeing the persistence. You're accumulating a lot of signal as you scan across toward this end. And then you see that over here as well. So how can you handle this? You can high pass filter. So you can take each of these scans and you can actually say, okay, I'm going to apply a high pass filter to this. And I'm going to go ahead and I'm going to get rid of my gradient here in my signal. And then when I combine these, I get this. So that's a fun, it's actually a Fourier analysis. So this is another Fourier technique, is to do this high pass filtering. And then finally, angular differential imaging. This is a fun one too. So here's a star, and we're obviously often very interested in finding planets and little stars orbiting other stars. And sometimes we want to actually take a picture of them instead of just indirectly observing them. And that's hard to do, however, because we have an atmosphere and the atmosphere blurs our images. So what we can do is we can take a set of very short exposure images. And in astronomy, you have to have a field rotator that rotates your image plane because the Earth is rotating. So you have to compensate so that your stars don't get all smeared out on your detector. What if you turn off your field rotator? If you turn off your field rotator and you take a sequence of very short exposures, like let's say, 50 milliseconds or so, this red thing is a planet. Well, the planet is going to appear to move across your field during these short exposures because you've turned your field rotator off. But what's going to stay constant is what's called the speckle pattern that's produced by your telescope and by just the like warm air around your telescope distorting your images and stuff. So what you then do is you take the median of all of this stack, and that's kind of like what your noise is, all your stuff that's not a planet or not a small star. And then you subtract that from all of these images. And so of course your planet didn't show up in your median because it's, you know, it's in a different place every time. So now we subtract the median from all of our images, and then we re-rotate those images. We go back and compensate for the field rotation. And now if you do that, here's the planet lined up, and then the messy speckles are gone and you can see it. And so here's an example of angular differential imaging. This is actually a little star, not a planet, that was found using this technique. And so that's it. That's my talk. Thank you.
Thank you. Questions?
First, just a fun comment that the first author of the paper there is a RIT PhD product. Supervised by the gentleman.
Yep.
Anyway, yes.
Yeah, I took this from the paper that was actually about RDI, a comparison between ADI and RDI, but yeah, I have to save RDI for another time.
Actually, serious question though, which is so you've got simultaneous activity indicator, which is the core of an absorption line emission or H alpha or something like that, and you've got the radial velocity. Is that coming from HARPS spectra? Is that what you're working from, sort of at the raw?
Yeah, so there are actually a lot of, Joel was asking about which telescopes are doing these measurements, and HARPS is one of them. We've worked with, this one I think is HARPS North actually. We've worked with HARPS South, HARPS North, high-res, Toll spectrograph, HRS spectrograph. We're getting data now from Espresso and Express. So lots of different ones go into these.
You have like some estimate how many target stars you've looked at so far that where you've been able to say, yeah, the planet's, you've been able to prove the planet's real or versus it's not?
I've published a couple, and this is not this one, but this one we're about to release. I have many more suspicious planets than I've actually published. I'm trying to tread a little bit carefully and, you know, not try to kind of call out everybody in the world for false positives, but I really do think there are a lot. I mean, I was telling Grover earlier, I think maybe up to 25% of the planets that we know about from radial velocities might not actually be planets. At least 10%, like based on the time series that I've looked at so far, which is in the tens of time series, you know, what I and my group members have done.
It's getting less and less likely there are intelligent civilizations.
Yeah, I'm sure there are. It's just really hard to find planets using this. Yeah.
But just a question. One of my takeaways from your talk is that these the finding these planets is very subtle, and you're looking at really tiny kind of quantities involved. And I'm just curious, is there a sense of what kind of signal and noise requirement is present on the original optical measurements in order to detect these minor variations?
Yeah, so we like to be above a signal to noise of 100 on each astronomical spectrum from which the velocity measurements are derived, and 200 is better. So you do need quite high signal to noise on the front end.
I was intrigued about the taper functions. I had heard about these orthogonal ones as fast. I looked at about, but based on orthogonal prolate sphere
Yes.
wave functions, which usually have different mode numbers.
Mm-hmm.
3 mode numbers for harmonic, spherical harmonics. So how much variability do you you have variability in choosing, you said you have to have different orthogonal ones for each different frequency, for example. So do you fine tune these mode numbers, or how is it that you just, how much flexibility do you have in how you design these orthogonals?
Yeah, so that's for this method is basically the shifts away from a uniform time sampling grid means that you get a different quality of information about every frequency, which means a different set of tapers. The thing that we fine tune is the bandwidth parameter. And so that is, I didn't show that here, but you can see the bandwidth marked on this slide. And so the bandwidth is basically, you want your spectral window to be a delta function, right? You want each perfect sinusoid to just yield a nice thin peak in the frequency domain. The closest you can get is a thin rectangle. And so the bandwidth is going to be the width of the rectangle. And so I marked that here with this vertical line right here. And so you can tune your estimate based on the bandwidth parameter. So if you narrow your bandwidth, then you get fewer tapers. Basically, you get 2 times n is the number of data points times w is the bandwidth. That's the number of tapers that you can get. And if you try to go to a higher number, well, too bad, your spectral concentrations crash to near 0. So if you want better spectral concentrations, like if you want all these numbers to be very close to 1 so that your spectrum has the least bias possible, you would narrow your bandwidth. On the other hand, if your priority is reducing variance, then you would widen your bandwidth so you can get more tapers and average together more independent power spectrum estimates. So it's a trade-off. Like, do you want better variance properties or better bias properties? Multitaper is better than the naive periodogram with both of those things, but that's what you tune is the bias variance balance. And you can actually, this is recommended, you can do several different power spectrum estimates from the same time series using different bandwidths. And that can be a really good way to kind of sanity check. What do you get? Does this make sense, etc.? So that's how we tune it. And when we do this, different tapers for every frequency, they all have the same bandwidth. That's what they have in common.
You've looked at data sets from a bunch of different exoplanet spectrographs. Do you have any preference for which one gives you the better data? There's a lot of competition between them as to who calculates their data the best. And
I don't want to put anything about that in print. Like I want to be really agnostic about that, but I really like what we get from Espresso is great, but from Express, because the Express team is measuring not only the velocities, but a whole lot of activity indicators. So I showed S index and H alpha, but they've also got sodium and ionized helium and, a bunch of other stuff. So you got a lot of information coming out along with the radial velocities. That's really helpful. So the fact that that team is doing that, I think that's great. I think the precision of Espresso is a little bit better than Express on the RV side. But I think leveraging the additional information on, the activity side, I think that more than makes up for it.
if not, thank you very much.